To make raw data useful, we have to enforce order. In computer science, that means taking chaotic, randomized structures and forcing them into predictable sequences. We will build analytical models using this simple dataset, an array of 5 unsorted integers: 14, 33, 27, 35, and 10. The goal is a state where every element is less than or equal to the one on its right, terminating perfectly sorted. But we have to execute this transformation under a strict mechanical constraint. The computer can only use comparison-based operations, meaning it can only evaluate 2 elements at any given moment. To solve this, we will examine the mechanics of 2 foundational approaches: bubble sort and insertion sort. Both algorithms share a mathematical limit. They operate with an average and worst-case time complexity of big O of n squared. While this quadratic time limit makes these algorithms unsuitable for massive datasets, they demonstrate how 2 different sets of rules can lead to the exact same efficiency limit. We start with bubble sort. Its defining mechanic is straightforward. It achieves order by comparing and swapping immediately adjacent elements. Looking at this diagram, the algorithm starts at the beginning of the array, evaluating index 0 and index 1. Since 14 is not greater than 33, the condition fails. No swap is executed, and the elements stay put. The pointer then advances 1 step to the right to compare 33 and 27. Here, the condition is met. 33 is larger than 27, triggering the algorithm's swap protocol. The computer physically swaps the 2 values in place, pushing the larger number right. This source illustration shows the rest of the first pass. The algorithm continues evaluating pairs until it hits the current maximum value, 35, and moves it to the end by swapping it with 10. That completes iteration 1, establishing the core bubble sort invariant. At the end of every full array pass, the largest unsorted element is guaranteed to be locked into its final correct position at the far right edge. As the diagram continues downward, subsequent loops repeat this exact process. The algorithm locks the next largest number into place, steadily expanding a sorted zone from right to left. There is a built-in optimization here in the C code. By tracking state with a Boolean variable, if the algorithm completes a full pass without making a single swap, it knows the array is completely sorted and breaks the loop early. That is the complete bubble sort strategy. It moves maximum values across the array boundary into a shrinking, unsorted zone. Insertion sort takes the opposite approach. Instead of moving values to the end, it maintains a strictly sorted sublist that grows from the beginning of the array. Let's look at an expanded dataset for this model. As you can see in the top frame, the algorithm has already established a small sorted sublist on the left edge, containing 14 and 27. The active problem is right next door. The algorithm selects the first unsorted value, the number 10, and needs to evaluate where it belongs inside that green sorted sublist. This is where the mechanics diverge. Insertion sort doesn't use adjacent swaps to find order. It scans the sorted portion to find the specific hole where the target value belongs. Processing the number 10, the algorithm evaluates it against 27 and 14, detecting that 10 is smaller than every item currently residing in the sorted section. To insert 10 at the very front, it has to perform memory shifting. The algorithm takes the element in its way and slides it 1 index to the right, leaving a temporary vacancy in the array. Because 10 is smaller than 27 and 14, those values are also systematically shifted to the right, migrating that empty index step by step toward the front. Once the correct position is clear, the algorithm drops the target value of 10 straight into the newly opened hole. This brings the array to a new, stabilized state. At the bottom of the diagram, we now have a perfectly sorted sublist containing 4 items. Insertion sort replaces adjacent swapping with targeted sequential shifting to build its sorted section. If these manipulation strategies are mechanically distinct, why did they yield the exact same big O of n squared worst-case performance bottleneck? This snippet of the bubble sort C code reveals the structural cause. Notice the nested loop, an outer for loop directly containing an inner for loop. The outer loop controls the total number of passes over the array, while the inner loop dictates the specific comparisons per pass. Because both of these tasks scale with the size of the input, the workload multiplies. We can locate that same setup in the insertion sort code. Halfway down, there is a main for loop wrapping an internal while loop that controls the shifting hole position. The similarity is structural. Despite their differing strategies, both algorithms require an inner iteration nested inside an outer traversal to properly sort the array. When traversing n total elements and multiplying that by up to n distinct operations inside an inner loop, the execution time creates a steep quadratic curve. Relying on nested loops to process every element is the primary reason for this quadratic complexity. At a high level, every algorithm we've analyzed works by dividing the array into sorted and unsorted sections. Bubble sort builds this sorted section at the right edge, moving the largest values upward. Insertion sort builds its sorted section at the front, integrating elements one by one into the sublist. A third approach that relies on these same sorted and unsorted sections is selection sort. Instead of shifting neighbors or bubbling values, selection sort scans the unsorted segment to locate the absolute minimum value and immediately swaps it to the front. Modern software relies on highly optimized O(n log n) algorithms for efficiency, but these quadratic, n-squared methods are the bedrock of learning algorithmic logic. Mastering the precise mechanics of how arrays swap and shift elements provides the logical foundation required to engineer advanced data structures.